All right, so this is the graph that you should have. So you should be looking at an exponential function. I laid out the points that I mainly use to graph, and then I just knew the general shape was going to be this curve. So the next component, and the reason why I listed out the points is because now it's saying we want to graph the inverse. So if you think back to I think maybe last week or the week before, when we talked about inverses, we talked about that the domain and range switch places. In other words, whatever is in the location of x is now going to become a y and vice versa. So if I have ordered pairs, I can go ahead and just switch those around and then use those as points to graph. So for example, the point 1, 1, if I switch the 1 and the 1 around, would still be at 1, 1. So I'm going to graph a point there. If I want to switch around the point 0, 1/3, that would mean that I'd have the point 1/3 comma 0. So that's going to be about here. I'm just kind of estimating. The next one would be if I'm going to switch 2, 3 around, that'd be 3, comma 2. So I'm going to find 1, 2, 3, comma 2. And then lastly, if I switch around 3, 9, that would be the point 9, comma 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. So what you're going to notice is it's basically the reflected version of the graph that we have here. And if you wanted to get some more points, we could. But it should be a reflection over that line that we talked about, y is equal to x. So I kind of see that. So if I'm thinking about what do I notice, obviously we created a new graph. And so there has to be a way that I can describe something that would be considered the inverse of an exponential. So that kind of brings us to this idea of something that we're going to call a logarithm, which we will dig a little bit deeper into in a little bit. We're going to focus quite a bit on graphing for these next couple of days or the next 2 weeks. But then we'll kind of dig into like how do we solve logarithms or how do we do some simplifying. So just some basic characteristics of logarithmic functions, and then we'll go down here and define what that looks like. First of all, they are considered the inverse of exponential functions. So again, this relationship of switching the domain and range is something that's going to kind of hold true for logarithmic functions. They are still going to have a base like they did for exponential functions. And they're going to follow the same transformation rules. So down here, that will kind of be the application of that. So this is what we're going to consider. And I know this looks weird because you've never seen a function that looks like this. We're going to go through and talk about all the different components of a logarithm function. So read in the form of f of x is equal to a times log base b is how we read this, of x minus h plus k. So I'm going to go ahead and maybe use some different colors to identify each component. So I'm going to start with a. So kind of following the same system that you would have all the other days, there's really 2 roles that A is going to play. So first and foremost, A is going to be the determining whether it's a stretch or a shrink. So if A is bigger than 1, then it's going to be a stretch. If it's a shrink, then A has to be somewhere in between 0 and 1. So I'm going to put a 0 here. And then it also means that there could be a reflection over the x-axis, and that would imply that there's a negative in the front. I'm going to move on to B. So here's the B right here. B is going to represent the base for the function. And typically the base will be a number. It can never equal 0. So the base will never equal 0. It'll also never equal 1. But it could be a number other than those. And it typically is not negative. So just kind of keep that in mind. let's see. I'm going to do h next. So h is going to represent, hopefully you are filling in the blanks, that's going to represent a horizontal shift. And keep in mind that it kind of goes backwards from what you would initially think. So if you see a minus sign, that actually means we're going to the right. So we're going to be shifting my function to the right. And then if I see addition, that actually means I'm going to be shifting to the left. And then lastly, the k is going to represent a vertical shift. And this one does kind of follow the typical pattern. So if you see a plus a number, that means up. And if I see minus a number, that means down. And then if you're curious about just kind of the standard x's and y's, or x's and f of x, then maybe I'll just use this color. X is always going to represent the input for the function, and then f of x is representing your output. So if I put something in for x and I get something out, that's that relationship there. If you need to pause and kind of make sure that your notes are maybe color coordinated, please feel free to do so, and then continue on. We're going to work through some examples, and I would make sure that you have your calculator handy for this. All right, so we're going to be graphing the function f of x is equal to 2 log base 10 of x plus 1. So just a couple of things calculator-wise. So I'm going to just show you my calculator. So if I turn it on, I'm on the home screen, and if you're doing a little bit of investigating, if you look down in this left-hand column, you can see a button that says log. If you press this, it's not going to show you a base. So anytime you're using something log base 10, this key on your calculator is appropriate. If, let's say, I were to change the base to something else, then there is a different key. So for our purposes today, we're just going to use things that are base 10. So this calculator key should be appropriate for most of the things that we're going to do today. So I'm just going to write a little note here. Even though it's not really a step, I'm just going to write down that log key on calculator automatically means log base 10. So that way we can use it to do some graphing. All right, so first we're going to name transformations. And then since we don't know a ton about how to solve, a lot of what we're going to do today is rely on our calculator. So I'm going to first start with naming the different transformations that I see. So I see a 2 here and a plus 1 here. So that means that there's 2 different transformations. So the first one, if a is equal to 2, that means that we're going to see a vertical stretch, meaning that that kind of like upside down graph is just going to kind of like get a little bit taller and skinnier. And then the plus 1 implies, because of its location, because it's by the x, is saying that we're going to be shifting. So shift left 1 space. So if you can kind of picture the basic one, we're going to be kind of like stretching it up a little bit and then shifting it to the left this way. So it may actually cross kind of like this central area. All right, so this is the easy part. From here, I am going to look for a couple things. I'm going to rely pretty heavily on the table. So just a couple of interpretations. If I'm looking for the x-intercept, remember that that means where y or f of x is equal to 0. So in other words, if I'm looking in a table, I'd be looking for where in that column for y or f of x do I see a 0. So I would say look for 0 in y column. Okay, so I'm going to do that. So I'm going to go to my y equals. I'm going to erase whatever else is in here. So it's using the previous function. I'm going to type in the function that we have here. So I have 2. Remember that log key right here is the one that we want. Even though it doesn't show the 10, that's the correct one. And then x plus 1, and then close the parentheses. And then I'm going to go to my table. And you might see some error messages, and we'll kind of dig a little bit more into that when we talk about graphing, but it looks like I have a point that's going to be at 0, 0. So that means that my x-intercept is at 0, 0. So I'm going to plot a point there. And then looking at the y-intercept, instead of looking for y or f of x equaling 0, this is where x is going to equal 0. So if, let's say, we did know how to simplify it, I'd find f of 0 and plug in the 0 here. But since I don't really know how to simplify this, I'm going to rely pretty heavily on my calculator. And again, I'm looking in the x column, and wherever there's a 0 there, that's going to then represent my y-intercept. So in this case, it just happens to be the same as the x-intercept, which makes sense because 0, 0 is the origin, so that would imply that it's both an x and a y-intercept. So I have this point here that's representing both the x and y-intercept, and then now I need to probably plot a couple more points just to kind of fully represent what my function looks like. So again, you won't be able to do this by hand, and as you can see, some of our numbers are going to be a little bit, we're going to maybe have to do some approximating. So just kind of do the best you can. Look for nice points, and if you can't find them, then we'll just have to use what we can. So I'm going to for sure use 9, 2. I might use 5 and 1.5-ish. And then maybe I'll use this 2, 0.9. So we're just going to have to get as close as we can to some of those. And then if you want to keep finding more points, you can. So 2.9, we're looking at almost 1. 1, 2, 3, 4, 5, 1, 1.5. So we're kind of here. 9, 2. And then as you can see, when we did like -1, there's an error. So that kind of tells me that when I get to this spot for x, I can't really cross over that. That's kind of what that means. So I'm going to draw my function here, and that's what it's going to look like for my logarithmic function. So if you need to, please pause. Otherwise, I'm going to show you another example that you can try, and then I will show the answer at the very end. So that says f of x equals negative log base 10 of x, close the parentheses, and then the plus 3 is on the outside.